Imagine a time before wheels, before writing, before even fire was fully mastered. What if I told you that one simple idea, a tangle of vines, transformed the way early humans hunted, built, and even survived? This is the story of how knots changed history. Throughout history, knots have been used for tasks like climbing or sailing. They were also used as religious symbols like the endless knot and the Borromean rings. A mathematical theory of knots was first developed in the 18th century by Alexandre Vandermonde, who discovered the importance of topological features. Topological features are characteristics of 3D shapes that are preserved despite deformation. In the 19th century, when mathematician William Thomson, better known as Lord Kelvin, proposed that atoms might be knotted vortices in the ether, when he observed smoke passing through a smoke machine in a specific geometric shape. Though this idea was ultimately disproven, it laid the groundwork for knot theory. Thomson's failed theory didn't deter mathematicians from pursuing the study of knots. Instead, it sparked a new way of thinking about how objects could be twisted, looped, and linked in three-dimensional space. This shift in perspective laid the groundwork for the development of the knot theory, an area of mathematics that intersects with topology, physics, and biology. Mathematicians began exploring the properties and classifications of knots, leading to the creation of intricate knot invariants and visual representations that revealed deeper insights into spatial geometry. In 1984, mathematician Vaughan Jones introduced a groundbreaking concept, the Jones polynomial. This new knot invariant not only provided a method to distinguish between different knots, but also had profound implications for physics, particularly in quantum theory. The Jones polynomial revealed a deep connection between knot theory and mathematical models in statistics and quantum field theory, bridging the gap between seemingly abstract mathematical constructs and real-world applications. Its introduction spurred significant progress in understanding topological quantum field theories and statistical mechanics, offering new tools to model complex systems. From the Jones polynomial, mathematicians derived a simpler invariant, known as the ARF invariant, which can only take the values 0 or 1. A knot has an ARF invariant of 0 if its path equivalent to an unknot, representing a trivial knot that can be untangled into a simple loop. On the other hand, an ARF invariant of 1 indicates that the knot is path equivalent to the trefoil knot, one of the simplest non-trivial knots with distinct properties. To illustrate, imagine a piece of string tied into a knot. If the knot can be smoothly manipulated, without cutting the string or passing one part of the string through another into a plane circle, then its ARF invariant is 0. For example, a figure 8 knot has an ARF invariant of 0 because it can be manipulated in this way. In contrast, if the knot cannot be untangled in this manner and resembles a trefoil knot in its essential structure, it has an ARF invariant of 1. Knot theory, originally a branch of mathematics, has found fascinating applications in chemistry. Chemists use it to study the topology of molecules, especially those forming knots or entangled structures. Synthetic molecular knots, like trefoils, are created through precise self-assembly processes and have unique properties, such as increased stability and reactivity. These knotted molecules hold potential in designing advanced materials, catalysts, and molecular machines. Knot theory also aids in understanding polymer entanglements crucial for predicting the properties of materials like plastics. By applying these concepts, chemists can innovate in material science and nanotechnology, leveraging the power of topology and molecular design. While much progress has been made, knot theory remains a dynamic and evolving field. The work of mathematicians has set the stage for further discoveries, not only in mathematics, but in areas like quantum computing, statistical physics, and chemistry.